So we have a problem here that is asking us to focus on the motion of a rock launched from the surface of the moon. And it says that the rock is 2 kilograms, reaches a maximum height of 5 meters, and is launched at an angle of 30 degrees, all of which we can see represented here to the right, our maximum height and our initial angle. And in this first video, we're going to focus on part A, which is asking us to calculate little g on the moon, otherwise known as acceleration due to gravity on the moon, which should be comparatively different to acceleration due to gravity on Earth, which is negative 9.81 meters per second squared. So obviously implicated by the question, we have to have some way of calculating little g. And to help us out, we're given a couple of initial values here, telling us that the mass of the moon is 7.35 times 10 to the 22nd kilograms, and the radius of the moon is 1.737 times 10 to the 6 meters long. So given this information here, and knowing that we have to find an acceleration value, the first thing we should do is turn to our lovely friend, the force equation, which is force equals mass times acceleration. And since our acceleration is actually acceleration due to gravity, we can change this to better fit what we're looking for. The force due to gravity, little g, is equal to mass times acceleration due to gravity. And we can subscript this to acceleration due to gravity on the moon. And so we have an equation that fits what we're trying to look for, acceleration due to gravity, but we need another equation, supposedly something that should fit what we're given here, the mass of the moon and the radius of the moon. And it's something we've just recently started talking about. Another force due to gravity equation, and this one is dubbed the Newtonian force due to gravity. And we can write out this equation in full. The Newtonian gravitational force is going to equal negative big G, which is a constant, times the mass of the moon times the mass of your object, or the rock, divided by the radius of the moon squared. And this equation allows us to put our moon mass and our moon radius to good use. Now we have a way to fit these two together, because once this local gravitational force equation is set equal to the Newtonian gravitational force equation, then we have a way of calculating the acceleration due to gravity on the moon, so that we can say locally the acceleration is an accurate value. So let's go ahead and rewrite these two equations so that they're set equal to each other. The mass of the rock times the acceleration due to gravity on the moon is equal to negative big G constant times the mass of the moon times the mass of the rock, all divided by the radius of the moon squared. And before we do anything else, we should probably point out that the mass of the rock here is on both sides of the equation in the numerator, which means that we should be able to cancel these out, and we won't have to worry about the mass of the rock. And so what we're left with is what we're looking for, acceleration due to gravity, a constant, which we will write out in just a second, the mass of the moon, which we were given, and also the radius of the moon, which we were given, which puts us in a really good place so that we can solve for what we're looking for. So then let's just write off here to the right, say that our big G constant is equal to 6.67 times 10 to the negative 11th power. And this is just a constant that can usually be given to you, so don't worry too much about memorizing it, but that's just coming from me. So anyway, let's get our purple back, and we're just going to rewrite this, and now we are going to replace these variables, all three of these variables, with the numbers that we know. So acceleration due to gravity is equal to negative 6.67 times 10 to the negative 11th times, and then the mass of the moon is 7.35 times 10 to the 22nd, and then both of these are going to be divided by the moon radius squared. We can't forget that. 1.737 times 10 to the 6th squared. And then, of course, all there is left to do is to plug these values into your calculator. And I have already done this off screen, so I'm just going to say right off the bat that our acceleration due to gravity on the moon is equal to negative 1.62 meters per second squared. And so our rock launched from the surface will be accelerating downward, this negative value, downward at a rate of 1.62 meters per second squared. And with this value all solved out, we can now move on to the next video where we will be doing part B.